All right, students, this is Mr. Hatfield. I'm going to try to demonstrate to you some equilibrium point calculations. Equilibrium calculations are based upon chemical reactions. So here we have a reaction where hydrochloric acid is dissolved in water. Hydrochloric acid is a strong acid rather, and so virtually all the hydrogen and all the chlorine in the hydrochloric acids is going to be turned into separately charged ions. Hydronium, H3O plus, and the chloride ion, Cl minus. Now, since this is a strong acid, the value for that reactant for any strong acid will always be just 1. And since we're using water, it will be 1 times 10 to the negative 14th, which is the dissociation constant for water. So that being said, how would we set it up? Our general formula for a strong acid is as follows. Our equilibrium point, K sub EQ, equals the concentration of the reactants divided by the concentration of the products. Now again, when we're talking about the concentration of the reactants, the strong acid is always just 1, and the concentration of water is that acid dissociation constant. Here I'm writing 1e negative 14, but that just means 1 times 10 to the negative 14. This is not a negative number, this is a negative power of 10, which is just a convenient way to express a very tiny number of less than 1, which would otherwise require us to write, 14 zeros. I don't want to do that. So for a strong acid, the strong acid would always be 1, and the concentration of water would always be 1 times 10 to the negative 14th. For the others, we're simply going to invent some numbers. In one case, I'll use a decimal. For hydronium, I'll go 0.003, 0.003. And for the chlorine, I'll go ahead and I'll use a negative number, 1 times 10 to the negative 8. I should correct myself and say that's not really a negative number, a negative power of 10. Why am I using a decimal here and a negative power of 10 here? Why? Because they're both convenient ways to write down values for very small numbers. Okay? So if these are the given concentrations of the products, hydronium and chloride, and if a strong acid is 1 and the acid dissociation constant effectively for water is always 1 times 10 to the negative 14th. For a strong acid, we're ready to calculate. And it's just the product of the numbers on the top divided by the product of the numbers on the bottom. Now, a potential point of confusion, of course, is that these numbers represent the products of that particular reaction. So when we say the product of the top, we mean the product of the products. And when we say the product of the bottom, we mean the product of the reactants. Don't let that confuse you. The bottom line is it's just multiplication divided by another multiplication. So let's go ahead and do that right now. 0.0003 times 1e negative 8 divided by 1 times 1 to the negative 14th. And when we do this, we're going to get a positive number. In this case, the positive number, amazingly enough, is 300. Now, what does that mean? Well, it's a number that's greater than 1, right? Since it's greater than 1, it definitely means that we're dealing with a strong acid. And with a strong acid, we expect a number that's greater than 1. What does this mean? It means in this reaction, the hydrochloric acid is about 300 times more likely to break down into these ions than it is to not break down. Again, it's a large number. It's more likely to break down than not. Okay, so now what about, this is for a strong acid, so I probably should just say strong. But what about a weak acid? With a weak acid, the dissociation constant is probably going to be less than 1, but we're still interested in the question of how strong it actually is or isn't. So it turns out that for the weak acid, we don't need this. We don't need this. For a weak acid, the expression is actually a little simpler. We can just treat water as a constant that never changes. And so for a weak acid, it's always going to be the concentration of hydronium times some anion, which is negatively charged. Chlorine was the anion here, but it could be something else. And on the bottom is just the concentration of the acid. That's the general form. Let's now do a specific example, which is based upon an actual equation for a weak acid. Let's say we're dealing with ethanoic acid. Ethanoic acid is a weak acid, and it's an example of a kind of acid that's called a carboxylic acid. So let me give you that equation so that it stands out. We use a slightly different color. We'll have ethanoic acid, CH3COOH, and it's going to react with water. And one of the products will be hydronium, just like the previous example. And the other product will be what's called the ethanoate ion, which is simply the acid stripped of that extra hydrogen, and it now has an overall charge of -1. So if that is our equation for the weak acid, we now follow this formula. We don't have to worry about the actual concentration of water. We're just going to put the concentration of the acid on the bottom. Let's say that our numbers for both hydronium and the ion, let's say that they're going to be the same as these two numbers. But for the acid, I'm going to say that this particular acid is a 7 molarity acid. Okay? So for the acid, instead of having a decimal or scientific notation, we're simply going to say the molarity, and molarity is moles per liter. So with that being said, here's our model. Hydronium on the top, we're going to use the same number we had before, which was 0.003. Right? That's our concentration for hydronium. And for the ethanoate ion, we're going to say that's 1 times 10 to the negative 8. And now we're just, for the acid on the bottom, okay, we're just going to say 7.0 molarity. It's a 7 molarity solution. Okay, so again, this is the weak acid. This is the formula that we're following. And we're being told that the hydronium is 0.003, so we put that there. The anion is 1.10 to the negative 8th, we put that there. And then the original concentration of the acid is given in molarity, and we put that on the bottom there. And now we can just set this up and solve 0.003 times 1 times 10 to the negative 8. The whole thing divided by 7. Now, when we do this one, we're going to get a pretty small number. I could write it out as a decimal, and we would be here for quite some time. Or we could just write 4.3 times 10 to the negative 13. Now, what does this number mean? Well, if 300 greater than 1 for the previous example means that the acid is 300 times more likely to fall apart than not, well, this number is the number, the odds of it completely falling apart. And the odds of it completely falling apart are pretty darn small. And so what we see here is that the weak acid will not completely dissolve, will not completely convert into ions. And so we'll end up with a system where the reaction is actually, going in both directions. Because in nature, It's very rare that systems settle into such a perfectly balanced equilibrium that they become neutral or that they even achieve stasis where the concentrations are moving in any measurable way. There's always forces acting on real world systems. Again, a good analogy is like a river. Sometimes rivers flow fast, sometimes they flow slow, sometimes they have a lot of sediment, sometimes they don't, sometimes they're warmer, sometimes they're colder. They're always flowing downhill because gravity is always pulling downward. But other factors are involved in whatever is carrying the river, how much load the river has, how fast it flows. There's a lot of stuff going on. And the situation will change. The river will always be there. So it is with chemical systems with molecules moving back and forth in reversible reactions or in complex systems of multiple reactions. There's all kinds of forces acting at once. And it may never completely quit moving or changing, but it will reach a state that is relatively balanced and stable as long as it's not disturbed by any other force. In that case, with our equilibrium constant describes the most likely position of a particular substance in that chemical system. And that's all we're really saying. We're not really saying something absolutely fixed. That's the equilibrium constant just estimates what's most likely to happen. Okay? So strong acid, equilibrium constant greater than 1, very likely to completely ionize. Weak acid, a constant less than 1, often much less than 1. And so very unlikely to completely ionize and will probably be part of a complex system that will be interacting back and forth. Now, other wrinkles are possible, so I'm just going to briefly take this definition just for a weak acid, and I'm just going to point out that, yes, the K sub EQ does equal the concentration of the products, hydronium and some anion, divided by the concentration of the acid. Okay? And since that's true, by algebraic rearrangements, we can solve for any unknown. For example, if we wanted just to find the unknown concentration of hydronium, if hydronium was missing, then algebraically, if we were trying to solve for that, hydronium would equal our equilibrium constant times the concentration of the acid divided by the concentration of the anion. Right? It's just algebraic rearrangement. If we were trying to find the anion, then the anion would be equal to our constant times the acid divided by the hydronium. And if we were trying to find the original concentration of the acid, again, through algebraic rearrangement, K sub EQ would be on the bottom, and our hydronium and anion would be on the top. So that's how you would handle versions where everything else was given, but you wanted to find either hydronium or the anion or the acid. You just rearrange the expressions like so. And I hope that was helpful.